Okay, good. I'm seeing your chat things. All right, I hope everybody's doing okay, stuck in your houses wherever you are. So today the schedule's a little bit goofy because I wanted to give you time to watch the videos I posted recapping model testing. And starting Thursday, we're going to try to stick with a regular schedule of a 9:30 problem solving session, followed directly by office hours. As always, if you can't make office hours or you have questions at other times, just email me and we'll figure it out. So you probably got my email that the project was extended. It was due this coming Thursday, but I pushed that to next Tuesday. Next Tuesday, I'm going to also be assigning the next project. It's going to go out next Tuesday because the semester is actually it's going to be over before we know it at this point. I have your homework 4, I guess it is, graded. The grader finished that. He has the actual homeworks. It doesn't seem like there's a way of getting them to everybody. So I will, I think, make an assignment in my courses and post your grades there. I think that's probably what I'll do. So you'll have them online in my courses as one of the grades you have access to. Some students have redone their exams, midterms. I'm expecting maybe some others to do it as well. I think it's a good exercise if you feel like you didn't do well on the exam to go back through the videos and learn this stuff, because some of this may be on the final. When we get into propulsion, we are going to be talking a lot about lift and drag again. And so it's important to have those concepts in hand before we get into the propulsion lecture. And if you go through those videos and sit with the exam, I can't imagine that would take more than, I don't know, an hour and a half or so to do that and improve your grade. So just a advertisement for doing that. So this unit that we're in now is, and if you stop hearing me for any reason, just, you can pop your mic off and let me know, or type a chat. This unit's about estimating resistance. So we've gone into all the resistance components. And this unit is about putting them all together in the standard method. And so this first week is looking at using model testing to estimate total resistance on a ship. So this is the fundamental problem that we're dealing with. I should also, everybody can see my screen, is that correct? Someone could chat yes or no. Okay, thank you. Okay, I wish we could vote this way, it'd be good. All right, so everyone can see my screen, which is good. So the fundamental problem, we're dealing with a ship moving steadily at a speed v through the ocean. We assume there's no waves, so it's a flat ocean. It's infinitely large. The bottom is infinitely deep, so we're ignoring bottom effects, lateral effects. And what we're looking at is we're trying to figure out really what is the horsepower that we need to drive the ship at a speed v. So the engine produces some shaft horsepower. So that's the horsepower measured where the engine shaft comes out here. We have some losses through the transmission. This depends on transmission efficiencies, which are typically high. A lot of these larger ships are, in fact, direct drive ships. And then, so you have power, if you measure here, has some losses because of the transmission. And then we will have losses through the propulsion itself. And that's the subject of the next unit. Ultimately, if we trace these backwards, or I guess we can go forwards, we start from the shaft horsepower. We have some losses through the transmission. This leads us to the delivered horsepower, which is a horsepower measured essentially after the transmission. Then we have the efficiency of the propulsion itself, which we'll see depends on your choice of propeller or water jet. And then this leads you to the actual effective power, which is a power you actually have to drive the ship through the water. So this is taking all the losses out from the transmission, from the fact that when you actually try to propel the boat, you do a lot of other things like stir the water up or create drag on the prop that requires power to overcome, which isn't doing any useful work. And this effective power is equal to the total resistance of the ship times the velocity of the ship through the water. And so this is the resistance of the bare hull ship. So this is a bare hull ship, so ship without a propeller. This is typically how they're tested. It gets quite complex to test ships with propellers on them. And so when we get into the propulsion chapter, we'll see how you can take a model test with a hull with of a bare hull. You can get resistance measurements from that and make them useful, because what happens when you put the propulsion on is it kind of affects the flow around the ship. And so you have to take that into account, and we'll see those factors come into play in the following unit. But most model tests are bare hull, and so that's what we're dealing with. And we'd like to know, based on the model test, what the full-scale bare hull drag would be. And by bare, I mean naked, not the animal bear. And so, and v is the ship speed at which it moves. And so really what the point of this particular unit is how do we get to this RT? And so obviously it's pulling in all these pieces that we've been talking about, boundary layers acting along, so skin friction along the side of the hull, the wave drag acting on the hull. So that's a pressure component, but it comes fundamentally from having put energy into the wave field. And then the other pressure component, the viscous pressure resistance, comes from having separation in the stern of the ship, which leads to this non-zero pressure integral over the hull, and is a form of drag, and a significant form of drag in a lot of these marine vehicles, because they're not, ultimately not that streamlined. So we have these three drag components, and we talked about the physics of them in class. We talked about how we can do estimates of the viscous resistance, and we talked about how the wave resistance is really tied very strongly to the Froude number. And that's why in these model tests, we test them at the same Froude number. So at least the waves are similar. The wave field itself is the same on the model as it is on the full scale ship. So we have these pieces coming into play, and we're going to use the model to estimate some of them, and then we're going to estimate some of them externally, and then combine them back together to get the estimate for the full scale ship. I put a little lecture up about tow tanks. I'm just going to sort of say something quickly about that now. This idea that, contrast it with the idea of a wind tunnel, where you have, in a wind tunnel, you have in a wind tunnel, I'll just grab another slide here. You typically have a wing section in a tunnel, and the air is moving over this, and the wing section sits on a sting like this, and that sting can measure the force on the forces, I should say, on this. Typically you're looking at lift and drag forces are measured, and you can do other stuff like PIV and things like that. I put a little window on your tunnel, and you can do particle image velocimetry, all kinds of diagnostics, Schlieren diagnostics if you're doing supersonic flows. And so it's kind of convenient, and all you have to do is pump air or water around this thing, and you're good to go. Now, the case of a free surface flow, so you have the water surface like this, and you have a ship. If you pump, so if this is part of a big tank or a channel, if you pump this water around, it tends to get very noisy. The free surface is going to start getting noisy. It's hard to have a nice flat free surface. So what they typically do is keep the tank still, and then they tow the boat through the water. And so this leads to some pretty big apparatus, because you have to tow it for long enough that you reach a steady state. It takes a little while for the waves to form, for the boat to get up to speed, for the forces to reach some kind of steady state. And then if you have diagnostics on top of that, you need time to run your diagnostics. Now, in the wind tunnel, you could essentially run it, all for 8 hours and have your grad students in there doing their measurements, and then turn it off at the end of the day. For the water tank, you just have that amount of time between when it starts and when it stops to do all your data measurements, so resistance and PIV and wave cuts and boundary layer measurements. And so obviously it's quite hectic. Then when you're done, so you tow it all the way to the end over here, and then you tow it all the way back. And then you got to wait until the waves, which obviously it makes waves, and there's it generates currents in the tank. You have to wait till those all die down due to friction, and the wave absorbers take care of the waves. and then you restart the experiment. And so maybe you're running a different speed, or often you'll run the same speed 3 times in a row just to see, get replicates, to see what kind of range you're getting. And so that leads to these very kind of interesting apparatus, unique apparatus, which are really long compared to, here's the Iowa tank right here. It's 96 meters long, and it's got a 3x3 cross section. Obviously a narrow purpose-built room. The room looks like it was built just to hold the tank. And then this thing right here just drives along these tracks. You can see these tracks here on either side. And then operator or operators stays inside here, and they're operating the speed, setting the speed, doing all the diagnostics, et cetera. And so these things are very unique, whereas a wind tunnel, you could put lots of stuff in there and test it. This is really designed for model testing. Some of these wave tanks, including the Iowa wave tank, are also designed to set up so it can make head waves. So you can generate waves at one end that propagate down the tank, and you can drive the boat into the waves, or you can drive the boat away from the waves. And this can measure the forces on a boat in a head sea or a following sea. It's not big enough that you could do waves coming at an angle. There are special tanks for that. But these narrow, long tanks, really you can only do directly into or directly away from waves. And there you're testing the wave length relative to the model length. You're trying to keep that the same as the ocean case. Not all the water tunnels have, I'm sorry, the ship tanks have those wave generators or the capacity to do that, but the Iowa one does. And I'll mention quickly, we'll do a question about this today, but you're looking to deal with this blockage effect to make sure that this isn't too strong. And so if you think about this, is the same case with a wind tunnel, but you have a cross section of your wind tunnel or your water tunnel. In this case, if it's a tow tank, then the ship hull might look something like this. The maximum ship cross section might look something like this, and you want to make sure that that's less than 0.5% of the tank cross section. The reason is that if we do a top view of the tank here, here's the long tank, and if our model starts to take up a big chunk of that tank, let's say it just barely fits in there. Here's our ship model, and you have the water flows in and around, it gets squeezed around here. And it's that same, you start having the same effect as, in 2 train cars. I don't know if you've been on an Amtrak train that passes another one going the other direction, it actually sucks the trains together. So you start having an influence between the walls and the body itself, and it alters the flow around the vehicle, and you end up with a flow field which is vastly different than you would have in the open ocean. So they try to constrain the blockage effects. I put a link up on my courses. Actually, I need to double check that I did that. There's a body called ITTC. I've mentioned this several times in my videos, the International Tow Tank Conference. It's basically a standardization group to standardize all aspects of model testing, resistance scaling, all these kind of things. They have numerous publications, and they have these committee meetings, and they make these really definitive decisions about how to move forward. And that's to try to keep things standardized, to allow people to exchange data, have the data make sense to somebody else, to make sure everything's done in a uniform manner. And they have papers essentially show model testing, and they include in the process of scaling up the model how to account for blockage effects if necessary, to reduce the influence of the walls on the body itself. And so when it's less than 0.5%, those blockage effects tend to be pretty small, certainly negligible for our class exercises. If you're doing a real kind of engineering work where you've gone and spent $200,000 on your model test, then obviously you want to go into the accuracy of including for blockage effects. I think that's what I want to mention there. In this country, the very first tank was this one at Hoboken. In Hoboken at Stevens Institute of Technology. This was named after Ken Davidson, who sort of pioneered model testing here, originally in their swimming pool. And then eventually they made him a tank, or he made a tank. And there's 3 or 4 tanks that are still there now. High speed, low speed, maneuvering, waves kind of thing. One slide I think I forgot to go through in the recap, so I'll just mention it here, is just a quick slide about models. You're dealing with size ranges from about 1 meter to 10 meter. 10 meter because the tanks don't get much bigger than the Carderock tank. So you're kind of constrained about how large the models can be and still not have significant blockage effects. About $1,000 a foot. This is getting to be an antiquated number because a lot of the model construction is getting more automated than it was in the past. Various materials are made for making these models. And there was a question we had on homework at one point, and I want to show you what these things actually look like now, which are called turbulence stimulators. And the idea of turbulence stimulators is to try to make sure that the flow is turbulent on the hull. We've already seen that for the models are shorter and they move at slower speeds, therefore the Reynolds numbers are lower, and in many cases much, much lower than the full scale. And if our Reynolds numbers get in the range where we might have some laminar boundary layer and some turbulent boundary layer, then we have an issue, because what we will be doing in our resistance decomposition methods, we're going to be estimating the skin friction on the hull. And if you don't know precisely where the point of transition is, then it's very difficult to get an accurate estimate of skin friction on the hull. And the second kind of issue is that the full scale boats tend to be, I mean, for the most part, are going to be turbulent boundary layers. And so that influences the nature of the separation in the stern. And so if your models are laminar and your full scale vessel is turbulent, then you're really very far off in terms of mimicking what's going on from the viscous effects. There's no way to make it entirely the same because your Reynolds numbers are different, but at least you can make it turbulent. And so that's what these stimulators do. You can see on the bow of the sailboat here, it's like basically glue and just sand. On that is a sand strip. Here's pins on the very front of I'm not sure what model this is. It has a hard chine. You can see this chine here. So this indicates to me it's probably a high-speed boat. But you have these pins here, and what these do is they stimulate the boundary layer to become turbulent even at lower Reynolds numbers. So in the absence of these roughness with a smooth hull, they would not be transitioning in this location, but it forces an early transition. And so there's also in those ITTC documents, they talk about how to stimulate the boundary layer and how to account for the stimulation, blah, blah, blah. And so basically you're forcing an early transition, so you know that the boundary layer is largely turbulent, and then you can take the friction formula that we'll be using, which are designed for turbulent boundary layers, and use them with confidence. And that's the point of these. So these are quite common in the process of model testing. So the first method we'll be talking about today, and we're going to work a problem on this, is Froude's method. And this, and there's basically, we're contrasting two methods. This is not the standard method, but I wanted to do this because this is really for historical reasons, and it's important to contrast the two, because this was used up until, say, the 50s or 60s. This was widely used, and then they started realizing that it was missing something, that it could be improved upon, and that led to ultimately to the ITTC 78 method that we'll be talking about on Thursday. As part of your Thursday prep, you'll see that. So, but they're quite similar, and so I want to kind of contrast what's going on. So the idea goes back to the same premise that we started the semester out with, and we were talking about similarity analysis, that the total drag coefficient for the ship problem is dependent on two fundamental non-dimensional variables, which I'm certain you're familiar with now, the Reynolds and Froude number. If we could match both of these, then this would simply mean that the total resistance coefficient for the model is identical to the full-scale boat. And all we would have to do is measure the model drag, convert it to a total resistance coefficient. That would be the same on the full-scale boat, and then scale it up to full-scale resistance just by dimensionalizing it, and you're done. But we cannot match Reynolds and Froude. And so the only thing we can do, so what the decision that Froude basically made was to match the Froude and let the Reynolds go. And that is because what he assumed is he took the total drag coefficient. He said, okay, it's made of three pieces that we've been talking about this semester. Under his assumption, the pieces are a frictional component, which is dependent only on the Reynolds number, a wave component that's dependent only on the Froude number, and another component that tries to take into account the effects of separation in the stern, viscous pressure drag. And this he called a form drag. So he gave it the coefficient of form and determined that this was constant for a particular geometry. So obviously if you have a fatter, bloatier boat, it's going to change what that form drag coefficient is. But whatever it is, it's constant for the geometry. So it's the same on the model as it is in the full scale. And again, these are all resistance coefficients. So these are all non-dimensional. So this idea of separating these two out, friction and wave, based on Reynolds and Froude, we'll see in the standardized method that's used today, the ITTC 78. And even that comes with some, even that is somewhat problematic, because when you have a boundary layer, it influences the waves on the boat. And when you have waves, it changes the wetted area of the hull, which would influence the frictional drag. So clearly there's some interplay between those two. You can't fully decompose those. The friction is slightly dependent on the Froude. The wave is slightly dependent on the Reynolds. But to simplify things and actually make this a tractable problem, we have to make this assumption. And so both of them will make this assumption of dividing out the pieces based on the dominant non-dimensional variables that drive them. So we have this Reynolds and Froude idea, and again, this is the key. The viscous pressure is taken into account by the form coefficient, a constant form coefficient. Then what they do is they lump, what Froude does is he lumps together the form and the wave into one component called residuary drag. That's what this R is, residuary, or leftover. Think of it as leftover, residual. So CR is going to be the CW plus C form. And so that's really this end of the total drag coefficient is putting together in these two components here. Now, since the form drags are the same, coefficient are the same on model and full scale, and the wave drag is the same on model and full scale, because you're matching Froude. You're matching the Froude number on the model and full scale. That's Froude scaling. So because you have matching Froude and you make this assumption that the form drag coefficients are the same, then the residuary drag, which is the sum of both of those, is the same on the model as it is in the full scale. So the residuary drag is, again, all the drag minus, I guess it's the drag that's left over after you've removed the frictional drag from the total drag. Then we can just basically have a little bit of algebra, where we have our total ship drag coefficient is made up of this frictional drag coefficient plus the residuary drag, which again includes the wave and the form. And this is equal to the frictional drag on the ship, where my subscript S here is for the ship, the full scale. The subscript M is the model. So the full scale drag coefficient on the ship plus the residuary in the model, because the residuary in the model is equal to the residuary in the ship. These two things are equal. That's what we already showed. And then we have this residuary drag in the model is just the difference between the total drag on the model and the frictional drag on the model. So this is equal to the frictional drag on the ship plus the difference between the total drag on the model and the frictional drag on the model. And then we just do some rearranging, and we have that the total drag coefficient on the ship is equal to the total drag coefficient on the model plus, or I'm sorry, minus, way I've written it here, minus the difference between the frictional drag on the model and the frictional drag on the ship. Now, again, if we could match Reynolds, the frictional drag coefficient on the model and the frictional drag coefficient on the ship would be identical, and that red box would be 0, and you'd simply have total drag coefficient on the ship is equal to total drag coefficient on the model. But because we don't match Reynolds, what's in that box is non-zero, and therefore we have to account for that. Now that's going to be estimated. Those pieces are going to be estimated in the red box, and we'll see how in a second. Now in the standard Froude form, you also typically add additional drag coefficients. One might be for appendages. So for example, you're testing sailboats, and you test it in the tow tank with just the bare hull, without the keel on it, without the rudder on it. Because you want to see how it works with different keels and rudders, and it's going to get expensive to do that in the tank. Just tow the bare hull, and later on you can add additional drag due to those components. The other key one is roughness. So a real boat in the open ocean has biofouling. The hull will start to build up roughness over time. It's difficult to mimic that in the tow tank because you have something that's varying over time. So in the tow tank, you start with you use a smooth model, and you account for what's the roughness of a real ship just by adding on a standardized drag coefficient. And so there's some difference in the Froude method and the ITTC 1978 method in terms of how the roughness is treated. And we will look at that. Graphically speaking, it looks something like this. So these are coefficients times 10 to the 3. It's a little hard to see this. So times 1,000. So you end up with numbers that are like 2, 3, 4, rather than 0.002, 0.004. So this is typically how they're plotted. And on the bottom, I have log 10 of the Reynolds number. And so if you were to do an actual resistance test, of course, the Reynolds number of the model is smaller. So you end up with data that's sort of scattered over here. These are the total resistance coefficients measured in your model test as a function of the Reynolds numbers. In the Froude method, this is divided between two pieces, a residuary piece and a frictional piece. And the frictional piece we are going to estimate using a friction line. So we can draw the top of this, which is a function of Reynolds number. So we can draw the position of the top of this red section as touching on this friction line curve. You're essentially translating this blue arrow over to the full scale Reynolds number here. And it's these crosses, which I'll paint with this pink paint. These are what you're trying to estimate. You don't know what these are. We're trying to estimate what these are. And so this blue arrow, you're essentially translating over. That's the part of physics that it's hard to get at. It's hard to come up with a formula for what's the viscous pressure drag, what's the wave drag. It's complicated to model that. It's complicated to do CFD on that. So that's really what we're relying on the model tests to do, is to tell us that. And we will be in charge of estimating the friction. And so the frictional drag coefficient on the full-scale ship is this green line. We're going to estimate that. We're going to tack on this blue part, which we're essentially getting out of the tow tank. Because we can measure this, subtract out this red piece, and leave us with this residual drag, we could go through that exercise and then basically take that over here and then estimate this green, tack on this blue that we just brought over, and then any additional roughness that needs to be accounted for, and we're done. And essentially we have a total drag coefficient. And so I just listed a number of steps. Algebraically, you can just do it in one shot. It looks something like this equation right here. And that's what we'll be applying to scale up this value measured in a tow tank to get this value of the total ship resistance. And from there we can get the actual resistance of the ship. And that's what we'll do in our class exercise today. Now, I want to be clear, we've used in class Prandtl's friction line for flat plate assessments for estimating the turbulent skin friction to a turbulent boundary layer on a flat plate. So the early kind of attempts to do friction lines use something quite similar to that. And what they found was, because it really didn't take into account the curvature, the three-dimensionality of the hull, which we've seen, particularly with the X-foil simulations, that the skin friction distribution sort of deviate from a flat plate once you get some thickness to the body, so that it's accelerating in some section, decelerating in some section. That idea of using a flat plate starts to fall apart, particularly if you're trying to do something accurately. If you're trying to get an estimate, it's still pretty good. If you're trying to get an accurate assessment, it's not so good anymore. And so over the years, there were a number of these lines that were used. And on Thursday, I'll present sort of a little bit of history of them. And it actually depended where you were. The US was using something different than Europe. And there are these various, essentially, friction formula. We've looked at Prandtl's for turbulent. And what we'll be using for all our exercises in our class is what's known as the ITCC 1957 line. It was just established in 1957. And again, that's the International Tow Tank Conference. And it has this form right here. So it looks different, quite different actually than Prandtl. Remember Prandtl's, if I remember correctly, is 0.074 over, did I write it down? I did not, sorry. 0.074 over Reynolds number to the 1/5. So the functional form is quite different. This goes inversely as Reynolds number is the 1/5. This goes inversely as the square of some deviation between the log of the Reynolds, and 2. So they're quite different, but when you actually plot them together, and again, this is CF times 1,000 versus Reynolds over a pretty big range from 10 to the 5th all the way to 10 billion. You can see there's an intermediate range from about 1 million to 10 million to 50 million even, over which they're quite similar, and then they start to deviate. And so this is trying to improve what is going on in terms of model scaling. And I'll talk a little bit Thursday on how did they assess whether the scaling is working. I will talk about that on Thursday. So they make these assessments and say, okay, we're scaling, we're getting resistances that are higher than they should be or lower than they should be. And what they did is then they went back and made adjustments to these friction lines to try to improve those correlations, to make them work better. And I'll show you some of the intermediate lines that were used and have now been scrapped over the years. Some of the complications are that when early tow tests were done, they towed the boats, but the tow test data isn't the full resistance of the model, which would be useful. What they're presented as is, for example, a residuary resistance, what was left over after they removed friction from the model. But then you have to see, okay, what friction curve did they use to get to that residuary resistance? And it makes working with older model data kind of complicated because of this sort of transitional period when various friction lines are used. So for all our calculations in the class regarding model correlation, extrapolation stuff, we're going to be dealing with this particular line, which is written right here, is also in your book, instead of Prandtl. So I just want to make that point. So the Froude's method recipe, we're going to use this in a problem in a few minutes, is measure the total resistance in a tank, and this is done with a dynamometer attached to the carriage, which is towing the boat along. And so it doesn't reach full resistance right away. It might spike a little higher than the total eventual resistance, but then the resistance will reach some kind of steady state, and that's the value that's recorded for that model for that speed on that day. Then you convert this to a total resistance coefficient. So we take that total model resistance and non-dimensionalize it, as we've done all semester. Now it's important here is to use the density of the tank water, the speed of the model squared. So that's a dynamic pressure in the tank for the test. And so it's specific to the tank conditions, the model speed, the tank density, and the wetted area of the model. So we create a total resistance coefficient for the model. Then we need a friction coefficient for the model. And so we just use the ITTC 57 line with the model Reynolds number. So that's the model Reynolds number right there. And again, the Reynolds number for these boats is U, the velocity that it's moving, times the length of the boat divided by the kinematic viscosity. And so for the model, these will be model speed and length. And this nu here is going to be the kinematic viscosity for the tank. And so typically, well, not typically, what they always do is measure the temperature of the tank. If it is a seawater facility, which a few of them are, not many of them are close to the ocean, so they use seawater, then you also need to know the salinity of the water in order to get a very accurate estimate of nu. And that will give you the Reynolds number for that you use for the model, which you use in the friction coefficient for the model. Same thing for the full-scale ship here, except here we're using ocean salinity, ocean density, ocean kinematic viscosity for our Reynolds number right here. And then we compute the ship total drag coefficient. So this comes from our algebraic formula again. The total drag coefficient equals the total drag coefficient of the model minus this discrepancy between the frictional drag on the model and the frictional drag in the ship, which again will be different because the Reynolds numbers are different. Then we add on a standard roughness. For the Froude method, that roughness is 0.0004. That is a fixed number. For the case of the ITTC 78 formulation, or what's known as the form factor formulation we'll look at Thursday, it uses a little bit more sophisticated roughness allowance that takes into account people can actually put in what the expected roughness of the hull is going to be. And then you're done. You have the total, and then we compute the total ship resistance coefficient by essentially dimensionalizing this total, compute the total resistance of the ship by dimensionalizing the total ship resistance coefficient. But here you need to use the density of the ocean, which we've been using 1,025, which is a good approximation, the ship design speed squared, the ship wetted area, and essentially you're done. So that's the process. The process on Thursday will look, and this again is not what is standard today. This is historical, but I want to contrast this to show you what improvements they made. But it's quite similar. The steps are just slightly different from what's used today. And so what we'll do is we'll work some problems. We'll just work through one problem. There's a homework problem, which is quite similar to the problem we're about to work through, where you'll have to do it yourself with some different numbers just to get a feel for what's going on with the process. So what I'll do is I will go to the in-class problem. So I have this up on my courses along with the solution, which is, if it hasn't appeared, it will appear shortly after I do this. So you have the solutions as well. And so this deals with a naval combatant. You're given the length of the ship, you're given the beam of the ship, you're given the draft of the ship, a volume displacement of the ship, and a maximum sectional area, AXS, equals 96 meters squared. I just want to jump out for a second to the lecture notes just to make sure you know what this maximum area is. Sorry for the scrolling. So did I pass it? Yeah, so maximum area, this shows a ship here. If you watch, and hopefully you did review the coefficients of form I discussed in my lecture, block coefficient, prismatic coefficient, and maximum area coefficient. That maximum area is basically you're slicing the hull longitudinally, so it's a constant YZ slice. So at some location, some location of X, you're slicing with a YZ plane. And wherever you get the biggest area of the slice, that is your AX. And typically it's somewhere around the halfway down the boat, what we call amidships. It's usually a little bit behind that. So slightly aft of amidships is where the sectional coefficient is maximum, but it's never more than a few percent after that for typical boats. There might be some radical boat where it might be, but for typical boats. So that's what this AX is. And let me just go back to our lecture. So you're given what that sectional area is. And I state here that occurs at the same position where where the maximum beam and draft occurs, and a wetted area of the hull of about 3,000 meters squared. The design speed is about 11 meters per second squared. Again, that's for the full-scale ship. You're given the ocean conditions through which it's traveling, and that's necessary for computing the full-scale ship Reynolds numbers and for dimensionalizing the drag at the end. You need the density for that. The model tests are a 1/25th scale model, and which seems like a pretty strong model scale, but with a 142-meter ship, that's about what you're going to end up with. And a freshwater tow tank. The tow tank has a cross-section of 4 square meters, so it's a 2x2, let's say, tank. And kinematic viscosity in the tank is about 1 × 6, and the density row tank is 1,000 because it's filled with fresh water, as most of the tanks are. So the first part goes through, it says, okay, so we want to get some coefficients of form for the hull. We will be seeing these more through the remaining weeks of the semester because there's been a lot of effort of really tying drag coefficients to the coefficients of form to understand how, when you vary the block coefficient, what happens to the total drag when you vary the prismatic coefficient. And this allows designers to make changes to the boat to improve upon the resistance characteristics once they make this understanding. And actually this should say CX, sorry, CX for the hull. The coefficient for the maximum transverse area for this hull. And so we have CB, block coefficient. This is probably the most important form coefficient, the block coefficient, which I went over in the video. And this is, again, just the ratio, the actual immersed body of the hull, nabla, which was given in this problem, divided by the box in which that exactly sits. So the box has to be equal to the beam of the boat times the length of the boat times the draft of the boat. So that is the block coefficient. And so if the boat was a barge, a rectangular barge, like the ones that carry oil back and forth through Buzzards Bay, the block coefficient is basically 1 in those barges. They're close to 1. But real boats have to be streamlined, a bit more streamlined. And so they aren't built like a box, and you're going to get some number less than 1. For this particular case, if you plug our numbers in here, we have, what was our 8425 divided by 142. That's the length times the beam, 18.9 times the draft, 6.16. And this is going to be equal to 0.5. I think I got 0.51. So that's a lower block coefficient, a bit lower than, say, a cargo ship. And this is more akin to what you would see in a naval combatant, which is a bit more streamlined, has more pointy ends, particularly the bow is pointier than the cargo ship. So you have a higher, a lower block coefficient than a cargo ship, but a bit higher than, say, a sailboat. The prismatic coefficient, CP, is the ratio between this displaced volume, the immersed volume of the hull, and a prismatic form. And maybe I will just pop over to show that looks like. Prismatic coefficient, you take this maximum area, sectional coefficient, and just extrude it like you're using whatever CAD program you guys use, I have no idea. Extrude it back and forth to create a prismatic volume in which this boat can fit, because you use the maximum sectional form and you extrude it the full length of the boat. Obviously that prismatic volume is smaller than the box or block that you use for the block coefficient. So we're going to end up with a higher value for the prismatic coefficient. So then that is going to be equal to this over AX. That's at maximum sectional area times the extrusion distance L. And this ends up being 0.618. And the last one is this sectional area coefficient, in this case maximum, what we call CX, which equals AX over BX times TX. And what this pertains to is you have some sectional maximum section of the hull, might look something like this. And at that position of the maximum section, you take the beam, which is this distance from here to here, and that's BX. And you take the draft, which is the draft at the position of that maximum section, which is TX. Now in the text above, I noted that the maximum section occurs where the maximum beam B is and the maximum draft T is. So BX and TX are just B and T for this particular case. In most cases, it'll be close to that, BT. And you're essentially saying how much of this rectangle is filled up by that section. And that, for this case, ends up being 0.824. Equals 0.824. And when you look at boats, you see all kinds of sections used. Cargo ships tend to use very, U-shaped sections with fairly hard corners like this. So their sectional area coefficients are quite high, whereas boats like destroyers or sailboats tend to use rounder cross sections. So their sectional area coefficients are lower than the cases of cargo ships. And again, it's always a trade-off of, what's the practicality? We might incur drag costs, but at the same time, we can hold more volume, which will, have bigger payoff in terms of shipping costs or shipping revenue to overcome the additional fuel needed to overcome that resistance. So compute the model dimensions. So I want to know the length of my model, the wetted area of my model, and the displaced volume of the model. So this gets into the geosimilarity rules that we had. So this is a geosimilar model, similar, and lambda was equal to 25. Yep, it's a 1/25th scale model. So all the length scales, including the actual length, are just simply going to be a lambda less than the full scale ship. So LM equals LS over lambda, which is equal to sorry, 5.68 meters. So it's a pretty big model. That's a pretty big model, but you can see with 1/25th scale, which is a vast, and you think about the difference between the full scale ship and the model ship, it's significant. We end up with still a fairly large model. This couldn't be tested in any given tank. You'd need a big tank. You have the wetted area of the model, and oops, I wrote that wrong. Any area, cross-sectional areas, surface areas of any kind, scale as the scaling parameter lambda squared. So the wetted area of the model is equal to the full scale area of the model, SWS, I think I call it, divided by lambda squared. And lambda squared in this case happens to be 625, that's 25 squared. And you end up with a wetted area of the model of 4.71 meters squared. And finally, the immersed volume of the model, nabla M, is as any volume on the model. Could be the volume of the immersed volume of the hull, could be the volume of the superstructure. Volume scales as scaling parameter cubed. So this will be the full scale ship divided by lambda cubed. And this value ends up being 8,425 divided by lambda cubed is 0.540 meters squared. Now, one of the exam problems showed that with Froude scaling, that the wave drag scales as with the volume of the hull. That was one of the things we worked on in class. The wave resistance scales with the volume of the hull. And so you can see here the wave resistance, in this case, we would expect in the model to be 25 cubed times less than the full scale. The skin friction scales somewhat with close to the surface area of the hull. Skin friction is all about surface area, or wetted area, I should say. The wetted area of the model is lambda squared times less than the full scale. So we can see here that on the model, we're expecting a higher fraction of viscous resistance than full scale resistance because, a higher fraction of friction resistance than wave resistance because our displacement went down by lambda cubed, but our surface area only went down by lambda squared, which tells us that we're not going to get the same ratio of skin friction to wave resistance on the model as we do on the full scale. Models have higher fraction of friction resistance relative to total resistance compared to full scale. And this is just the nature of scaling these two things. So we will see that when we look at the, when we construct the actual values in a second. The blockage ratio. So for blockage ratio, we're given that the tunnel cross section, or the water tank rather, is, I think it was 4 meters squared. And we had a maximum cross-sectional area. So this is a transverse view showing the model coming at you. The actual AX, so I guess we got to compute that, don't we? So AX for the model. So AX for the model is equal to AX for the full scale ship divided by lambda squared. Again, any area of any kind, as long as you're talking about the same thing on the model and full scale, because they're geosimilar, it scales as lambda squared. So this will be 0.154 meters squared because we were given AXS and we know lambda squared is 625. And therefore our blockage ratio, I'll just call it BR, is equal to AXM divided by the tank cross section, which is 4 meters squared. And that works out to 3%, something like that. We'll call it 0.04. So we're at we're less than 5% in the tunnel, but it's getting to be what I would call a high blockage ratio. So this might be a concern. I would say this is a concern. So that gives you an idea of how to compute that. And the model speed, this is a really critical thing, of course. So we're using Froude's method, what he referred to as the corresponding speed. And again, this was the big difficulty in early model testing was what speed you run the model at. Some people thought you just run at the same speed as the full-scale ship. Some people thought you run at a speed equal to the scaling ratio. So in this case, 1/25 of the full-scale ship. But neither of those really worked with the physics. And what Froude determined was when you run what he called the corresponding speed, that you get the same wave pattern. And that's what we do today. Now we call it matching Froude number. So we say Froude number of model equals Froude number of full-scale ship, or U model over root GL model equals U ship over root GL ship, or U model, which is what we want to know, is equal to U ship times the square root of LM over LS equals, and the square root of LM over LS is 1/5, because the square root of 25, or square root of 25 is 5, and this is the square root of 1/25, equals US over 5 equals 2.24 meters per second. So we can see the model speed is less than the ship speed by a factor of 5. The model is shorter than the full-scale ship by a factor of 25. So we can already see that the Reynolds number of the model is going to be much smaller than the full-scale ship. So this is again the corresponding, what you call a corresponding speed, matching Froude number. You come up with this calculation. So this is a good thing to at least know that comes directly from the Froude number, and it's a good thing to kind of memorize or just have in your head at least. All right, so the last thing we want to do is actually use Froude scaling to scale up the Froude number, the total resistance. So you're given here that the model total resistance in the test is equal to 54.41 newtons. And we're going to use Froude's resistance extrapolation method to compute the effective power. I should write this as PE, the effective power of the ship in kilowatts. Actually, I don't think I actually did that, but in kilowatts using Froude's resistance extrapolation method. So this goes back to that recipe. And so the recipe is, hopefully I'll get the steps right, but the first step is we need to compute the total resistance coefficient of the model, compute CTM. So we have RTM, we need CTM. So CTM is going to be RTM divided by 1/2, divided by our dynamic pressure in the tank. So that's 1/2 rho tank times U model squared. We know all these things. Rho tank was freshwater again, so it's 1,000 kilograms per meter cubed, times the wetted area of the model, which we computed in, I think, part B or C above, times SWM. And this gives us a resistance coefficient of 4.59 e to the minus 3. And if I write it as times 1,000, it would just be 4.596. So that's the total resistance coefficient of the model. And now we need to know the friction coefficient on the model. And this is going to be using the ITTC 57 line. So we need to know the Reynolds number of the model. And that's going to be U model, L model, divided by nu. I left nu the same for both cases, but we'll put nu, I'll put nu tank here, because this would be the kinematic viscosity of the tank. If we had some precise value, and again, they measure the tank temperature during the tests to get that nu. There's standard formula online. You can look up for fresh water, what the kinematic viscosity is a function of temperature. In fact, there's some MATLAB codes that can do that for you. And we have the model is 12.72 million. 12.72 million. So it's a fairly high Reynolds number for a model because it's a big model. It's 5 meters long. Most of the, when we look at the systematic series starting next week, we'll see that a lot of those systematic series model lengths are around 2 meters, somewhere around there, or more typical lengths used mostly to keep costs down and because of the tanks that they were run in. So CFM, we're going to use this ITTC 57 line. This is going to be 0.075 divided by log 10 of REM minus 2 squared. Okay, and so we're going to plug in that value there, and this will be equal to 2.878. So if we wanted to at this point, we could compute the residuary drag on the model by taking this total 4.596 and subtracting 2.878. That would be the residuary drag. But the algebra means we can basically skip that step and get right to what we really want, the total drag on the full-scale ship. So we also need to know the frictional drag, or estimate, I should say, the frictional drag on the ship. Also going to use the ITTC 1957. The only difference being here, we need the actual Reynolds number of the ship. RE ship is U ship, L ship, divided by nu, and I'll just put C here, CSW for seawater. And again, in this problem here, I gave you the same nu for both, but in general, they may not be the same, so just be cautious about that. And we have 1.59 billion is our Reynolds number. Plug that into, I won't write the formula again, but this gives the CFM is equal to, CFS is equal to, what is it equal to? 1.446 e to the minus 3. So whereas the residuary component, which includes the wave, is the same on both, we have that this frictional component on the ship is less than it is in the model, which tells us here that the wave is more, relatively speaking, more important on the full-scale ship than it is on the model in terms of the overall drag, as I mentioned before. All right, and so now we have, I think, all our pieces. I may have our step numbers, might not quite be like the recipe on that I showed you before. I apologize if that's the case. We have compute, yeah, in fact, step 1 should just be measure the model speed. So this is really 2. If we want to keep it like our recipe from 4, 5, step 1 is actually just measure the resistance. 5 is our total ship coefficient without any added roughness. I'm sorry, added drag coefficient, I should say, CTM, minus this discrepancy between the model and the full scale. I'll caution you, sometimes you see this formula written where they put a plus here and they switch these two. So just bear that in mind. Bear in mind that whatever you've written here should result in a lower total drag coefficient for the ship than the model. So whatever you're subtracting off here should be a positive number. So you have CFM, which is greater than CFS, will have a positive number from what's in that parenthesis. And this is going to be equal to 3.16 e to the minus 3. Excuse me. And this is the total ship drag coefficient. You can see that it's less than the total ship drag coefficient of the model, 4.596, 3.16. Of course, this does not mean the total drag is less. It's the drag coefficient. Our next process will take us to the total drag. Oh, actually, we got to do one more thing. We're going to add the standard roughness for the Froude method. So I'm going to say CTS equals CTS plus delta CF. And, well, I'll just write it here, equals CTS plus 0.0004. So now we're up to equals 3.56 e to the minus 3. And you can see here that roughness is not negligible. And then finally, we need to compute an actual resistance, get away from these coefficients. RTS is going to be equal to CTS times the dynamic pressure in the ocean, so seawater, times the U ship squared, there's a dynamic pressure, times the wetted area of the full-scale ship. We have all those numbers. So for seawater using 1,025 kilogram per meter cubed, the ship speed was given, that's the design speed. Wetted area was given, and we just computed CTS, and it gives us a total resistance of 675 million newtons. I'm sorry, 675,825 newtons. And now we can compute the effective power. So the effective power is the barrel hull resistance, which we just computed, times the speed of the ship. That's the power that we need, the actual propulsion to give us to move the barrel hull through the water. And so this works out, just multiplying these two together, which I have, to about 7.56 megawatts. I think I asked for the answer up there in kilowatts, but I'll write it here in megawatts. And this works out to about 10,000 horsepower. I think it's like 10,100 horsepower. So, but a big vessel, so a lot of horsepower, a lot of megawatts of power. And this is to move it at its design speed. So essentially we used Froude's extrapolation method. We started with the model resistance and we extrapolated up. And so it's essentially like a recipe. I'd like you to have a sense of what's going on in terms of what are the assumptions. So I'll just flash back to that and I'll stop the lecture. Again, in the Froude method, you have, apologize, I went past it. You have this idea that you're splitting the total resistance into a frictional piece dependent on Reynolds number, a wave piece dependent on Froude, and a constant piece. This is where it's going to get different when we get to the Hughes or ITTC 78 method on Thursday. So this constant piece to try to treat this third form of resistance, which is due to separation and boundary layer thickening in the stern. Then we lump these two, get stuck together because they're both essentially dependent, or both are going to be the same in the model and full scale. The wave drag will be the same coefficient because we're matching Froude. The form drag coefficient will be the same because we stated that it's constant for a given hull, and the hulls are geosimilar. So those are the same on the model and the full scale, whereas the friction piece is not. And so when we end up writing the total drag coefficient on the full scale ship, it's going to be equal to the total drag coefficient on the model minus the discrepancy between the frictional pieces. But those frictional pieces we estimate, and we estimate them using the ITTC 57 curve, using the specific Reynolds numbers of those two cases, where the model Reynolds number is a lot smaller than the ship Reynolds number. So we end up with some positive number in that box because frictional drag coefficient declines with increasing Reynolds number. And the result is that the total drag coefficient on the ship is typically less than that on the model, which is what you see here. And so we, in our little exercise today, we never explicitly computed, we could have, but we never explicitly computed the blue line, the residuary drag. We were given this, we explicitly computed this, we explicitly computed this, and if you're given the total drag coefficient and you explicitly compute this, you have intrinsically at your hand CRM, but all you're doing is essentially you're translating it down here, and you're just looking at the difference between this level and this level right here, which is the difference in the frictional resistance. You're pulling away from the total here, this difference, to shrink it down to here at this position here, and then you add on this delta CF to get back up here. That's essentially what the algebraic formula does. So the differences with the standard model, which we're talking about Thursday, are kind of subtle, but they're important. And really what the standard model decided, what they decided was that this piece here, this form piece, which has to do, think about a ship, top view, the flow comes over, and we tend to have flow in the wake here. The nature of that wake flow, in fact, I think I have a better shot of it in the figure. Let me go back to that. No, maybe not. The nature of the flow in the wake here depends on the Reynolds number. And so in Froude's case, in the Froude method, it's assumed that it does not depend on the Reynolds number, the nature of the wake, the type of eddies that are formed, how much separation there is. But the reality is, as we saw maybe in a really exaggerated effect with the golf ball or the cylinder we were talking about, the nature of flow separation on a cylinder is a function of Reynolds number. We looked in the very early part of the class when we were looking at flow over a cylinder, drag coefficient of a cylinder is a function of Reynolds number. We saw it's highly dependent, particularly in a particular region. It's very sensitive to Reynolds number. So the nature of flow separation, how much there is, which influences this viscous pressure coefficient, or what many people call form drag, is Reynolds dependent. And so what the improvement that was made was they came back in and said, this thing right here, we're going to make Reynolds dependent to try to make it a little bit more, the physics a little bit more accurate, with the hope that the model scaling procedure could be more accurate, that we could improve the process of taking models and scaling them up. The reality with all of these things is that the larger your model scaling ratio gets, the worse your approximation gets. So if your model's, for example, the same size as your full scale ship, then you get a perfect representation of the full scale drag. As you drop that model scale down and the discrepancy between the Reynolds numbers gets bigger and bigger, then you start to incur errors because of the assumptions that are inherent in these processes. And so what they were finding is, in the sort of early days, the kind of rule of thumb was they didn't want to go below a third scale for the models. They started finding below a third scale, the errors just started swamping them. And they were getting incorrect numbers, incorrect answers. And as time went on, they improved the scaling procedure. And now, today they use these sort of 1/25th scale models, and they're getting information out of them that's useful for the full scale design. So Thursday, we're going to cover the standard at what is the standardized method. And it will look very much like this with just a subtle difference. And that subtle difference just means the form drag is Reynolds dependent, but it will also mean that we bring in a new parameter, which is the form factor K. And we'll have to talk about, okay, we've made it, the physics better. However, we've made things more complicated for ourselves because now we have another parameter estimate, and I'll talk about how to do that in class. So that ends the lecture. Are there any questions? You're happy you can go on mic or type them in. Any questions about the lecture, I should say, or this problem that we solved? If you have any, let me know. I'll give you a few seconds to type anything in. I don't see any questions. That's good. Maybe you're all asleep or watching YouTube. But anyway, we'll keep going. So my, all right, wide awake. So I will, I'm going to take like a 2-minute break. I'm going to leave the Zoom up, and the plan will be to transition to office hours. If you want to ask questions in office hours, you might as well go on mic for that. I will run that until 12:45. And again, if you can't attend that, as some of you may have class right now, I don't know, then that's a good question. The office hours will be recorded. I have not done this recording with Zoom before, but Patrick asked if it's being recorded. The answer is yes. I haven't dealt with this, so what I will probably try to do is pull the recording down and cut it into, and cut it into the lecture piece and the office hour piece, if you want. If during office hours there's something you don't want recorded, let me know, and I'll cut that piece out. Do people think the office hours being recorded would be useful? Is that why you're asking, or you prefer them to not be recorded?
I personally feel like it would be better if it was recorded.
Is there any opinion on that? No opinion? Okay. Okay. All right. Okay. Patrick's suggestion was to clip something useful. So if I go through something, so maybe if people are asking questions and they seem to be kind of persistent questions, that sounds like something that would be useful to clip, as Patrick put it. So that's what I will try to do. I've not done this before, so I'm not sure that's going to go, but I'll give it a try. Usually I record using a different piece of software, but Zoom is recording at the moment. So in theory, I can do that. Okay, so I'm getting preferences about recording, so that sounds good. So we'll do that. It probably will be separated from the problem solving component somehow, and I'll figure it out tonight. Okay, and all right, give me 2 minutes because I have young children I have to tell what to do, and then I will start office hours, and they will run till 12:45. And again, if you have questions outside of that time frame, then email me, and we'll set up a private or a separate, I should say, Zoom meeting, which will look like this. You can ask me whatever you want. I'll answer. Well, I mean, within the context of the class, I'll answer on the iPad, or if it's something I think I can answer through email, I'll do it that way. And otherwise, so class Thursday is going to start at 9:30, and that's what we're going to try to do. So you already have pre-class prep video. It's a short one up there, just covering the ITTC 78 form resistance extrapolation method. Watch that before class on Thursday. I'm going to do a very quick recap of it, and then we're going to run through a longer problem than we did today. We're going to run a couple of data points to see how they show up for a model scaling procedure using the ITTC 78. That's Thursday. And then office hours will run directly after class on Thursday from about 10:15 to 11:30, something like that. And that should be closer for those of you, I know you have conflicts with another class now. If we start the problem solving at 9:30 on Thursday and we get into the office hours earlier, I'm hoping that will mean that more people could attend the regular office hours than could earlier this semester when we had regular, before the world went mad. So, okay, hope everybody's doing okay, not going stir crazy, and you can still go outside and run around, so please do that. And I will start office hours in 2 minutes, so give me a 2-minute break. No need to stay on. If you got other stuff to do, go do it. Thanks.
All right, while he's doing other stuff, can anyone hear my mic?